And with that, I'd like to turn it over to our last speaker. We have Dr. Piyush Jain coming to us from NRCan, Canadian Forest Service. And he's going to be talking to us now from a North American perspective and climate impacts on wildland fire, all things wildland fire. So over to you.
Thank you for the opportunity to speak today. So I have a confession to make, which is that I'm not going to be talking about fire emissions or black carbon, and I won't be focusing on the Arctic, but I will be talking about the fire and the climate drivers of fire from a North American perspective. And of course, all of these things are related. Okay, so wildfire in North America. So it's to understand fire in America, North America, you need to understand the distribution of fuels. So this is, on the left is a plot of forest cover where the canopy is at least 10%. And you can see there's an extensive boreal forest that extends from Alaska all the way into eastern Canada. And there's also temperate forests in the west, going down into California and other states on the Pacific Northwest. On the right, we see the area burned from the Modus area burned product, and we see the distribution there. This is the annual area burned. So there are regions, Alaska, going into the middle of Canada, Alberta, Saskatchewan, Northwest Territories, and then obviously Western North America, Western CONUS, including California and Oregon and Washington and so forth, where there is significant fire that occurs every year. And then we should also look into ignitions, obviously. So there are two main sources of ignitions for fires. There's lightning and there's human caused. So the left plot there shows the lightning density. This is just data from the Canadian Lightning Detection Network. So it cuts off at, I guess, I don't know, roughly around 40 degrees latitude. I don't have the data available to plot south of there, but you can see that there is lightning over most of the continent, and the density of lightning drops off as you go further north. Looking at population, obviously population is highly it's nearer to population centers in the east and on the west coast, but drops off quite significantly as you go further north. So what we find in terms of fires is that in Canada, we have 85% of large fires in Canada lightning caused, whereas in the US, because of the much higher population density, 84% of fires are human caused. So there's some other statistics here. In the US, they see 73,000 fires every year, with an average of 2.8 million hectares burned. And in Canada, we have 8,000 fires a year with 2.1 million hectares burned on average. In both countries, we see area burn is increasing. You can see the signal there in the United States is much stronger than in Canada, and is mostly driven by fire activity in the Western CONUS. However, if you do go back to 1959, there is a positive trend in area burned in Western Canada. And then the season lengths are also increasing in both countries. There I have quoted 17% increase from 1992 to 2015 in the United States, and a mean season increase of 19 days in Canada. And of course, one of the drivers of these observed trends are fire weather, and in particular, extreme fire weather. So one number that we often cite in Canada is that 3% of the fires are responsible for 97% of the area burns. So we talk about the tail wagging the dog. And those 3%, those very, very large fires are driven by extreme fire weather. So this is some work we did for global fire trends recently. So on the left there, I'm showing 3 different metrics of extreme fire weather. So there's the Fire Weather Index, the Canadian system, and another output of that is the ISI. So Fire Weather Index is related to fire intensity or potential fire intensity. ISI is Initial Spread Index, which is related to the potential spread of fires. And the bottom one is the vapor pressure deficit. So the vapor pressure deficit is the difference between the potential amount of moisture that an atmosphere can hold at a certain temperature and the actual moisture that it holds. So it's really a measure of the drying capacity of the atmosphere. So just zooming in on those trends on the right-hand side, looking at the vapor pressure deficit, the 95th percentile, annual percentile, and the trends in that over the last 41 years, we see there are positive trends over much of the continent, and those trends are strongest in Western CONUS and going up into the interior of BC. So, of course, there are many climate models that are projecting increased fire risk going into the future. But another way we can look at what we may be expecting far into the future is by looking well into the past. So if you go back to the early Pliocene, 5 million years ago, on the top left there are temperature reconstructions. So the global mean temperature was about 3 degrees higher than it is today about 5 million years ago. And the parts per million of CO2 in the atmosphere are also comparable, about 400 to 450. Right now, we're at about 414. And in fact, I just read in The Guardian yesterday, they've updated that to 417 parts per million. So today, the summer temperature is about 4.1 degrees in Eureka on Ellesmere Island. There's a picture there on the bottom left. And there's been some work done by one of my colleagues and others looking at this Beaver Pond site, which is a very fossil-rich site in Ellesmere Island. And you can sort of see the current picture of it in the middle there, and an artist's impression of what it looked like 5 million years ago. So it's very fossil-rich, and that includes evidence that there was large-scale boreal forest throughout Ellesmere Island, including pine, spruce, larch, birch, pollen, and that there was a lot of fire as well. So obviously there's a lag in the Earth system because of the latent heat in the oceans and ice, inertia of ice melt. But 5 million years ago, the mean summer temperature at the Beaver Pond site was estimated to be about 15 degrees Celsius. And today it's 4.1, but we have comparable CO2. So there's a lot of uncertainty about what the future holds, but I think it is useful to get some perspective by looking in the past. So these fire weather trends, we're generally looking at surface conditions. So looking at the smaller scale, less than a kilometer, up to sort of mesoscale weather systems. Another way of understanding the variability and the drivers of extreme fire weather and fire events is to look at the larger scale events, so the upper atmosphere, so-called synoptic and planetary scale patterns. And a lot of the work I do is in this area. Excuse me. So one of course, one of the things that has been observed in the last few decades is Arctic amplification, which is the fact that the very far north is warming at a much faster rate than the rest of the globe. So you can see some data from NASA there, where it shows that the temperatures are increasing much faster in the north, and up to 3 degrees in the last 70 years or so, compared with a mean annual increase of about 1 degree globally. So the Arctic is warming much faster. And one of the mechanisms that's been proposed as a result of that is the fact that the jet stream, which modulates much of the mid-latitudinal weather, is changing. So the idea is that as the Arctic warms, the jet stream becomes the gradient, the poleward temperature gradient between the equator and the pole decreases, and this makes the jet stream wavier. And a wavier jet stream means you have more excursions of tropical warm air north, and we may see more extreme weather in terms of heat waves and atmospheric blocking, and this obviously has implications for fire. However, looking at the literature, I don't think this question has been settled quite yet. On the bottom left, there's a couple of papers on the bottom there. One is evidence that the jet stream is becoming wavier, and on the right is another paper that says, well, actually the evidence is not there yet. So I think whether you believe or not that the evidence is there or that the signal is not yet emerged, in any case, the jet stream does modulate the mid-latitudinal weather patterns and therefore affects fire weather. So this is a couple of examples. On the left, we look at the 300 hectopascal wind speeds, which are about 10 kilometers up in the atmosphere. And those purple spots represent fire events, fire spread events. So these are two examples of quite extensive fire that occurred in North America. So 22nd of July 2007 is the top two panels, and the bottom two panels are June 2015. In fact, Rick's talk, he showed, I think, that 2015 was the second highest area burned on the record that they had. So this is partly because of this large June event where we had a double jet over much of North America. And in fact, we had a lot of fires burning through Northwest Territories, Alberta, and Saskatchewan, as you can see there. So, and on the right, we have the corresponding 500 hectopascal geopotential height anomalies, which are usually used by meteorologists to sort of correlate with the presence of highs or lows. So we looked a little bit closer at the polar jet stream and wildfires. So on the left there is all the so-called fire spread events. So what we do is we interpolate thermal hotspots. We define a spread day as any day where a fire grows more than 480 meters. We looked at all large fires in North America, so that is greater than 5,000 hectares. We found 9,480 such spread events from 2002 to 2016. And then what we did is for each event, we did a composite analysis looking at those upper area wind speeds or wind direction and the geopotential heights. And the main takeaway, I think, from those plots on the right is that each spread event is associated in general, or the mean tendency is to have a ridge which builds up before the fire event and then decays afterwards. And you can see that the red on that middle plot represents northerly flow of the jet stream, and the blue represents a southerly flow. So that's a ridge over each event. And on the right, you see that the geopotential heights increase around each fire event and then decrease afterwards. And another way of looking at these sorts of events is to track individual heatwave events through geopotential heights. So we look at persistence of these 500 hectopascal anomalies. So this is a little video here I'll play. This is the 2021 heat dome, in fact. So the blue outline is an algorithm which we've applied to track the heat wave using the geopotential heights. The large red triangles are any fires greater than 200 hectares, and the orange ones are any fires less than 200 hectares. So you can see that the heat dome was a very, very large event, started on the west and expanded and moved to the right, and a lot of the fire activity basically tracked with that heat wave event. Let's let it finish there. So looking at that 2021 heat dome event in the context of events in the last 40 years or so, that plot shows the largest event for each year, and also the grey dots show every other event. And you can see that that 2021 event really stands out as being a much larger, stronger event than any of the events observed in the last 40 years. So what we're showing there is the strength, which is defined as the amplitude times the size of the event times the duration. And so it was 190, it was almost twice as strong. It was 91% larger, and I guess it was 3 times as strong, and 44% longer duration than the average of all the strongest events in the previous years. And looking at trends at the various attributes of these heatwave type events, we see that there are generally small positive trends in the number, the duration, the area, and the amplitude. So these events in general are getting larger. they're getting more intense, and they're taking up and they're lasting a little bit longer. In particular, the 2021 event, what we can do is we can do this light attribution where we remove the thermodynamic climate signal and then recalculate the heat wave size. And we found that the 2021 event was 7% longer, 51% larger, and 64% higher amplitude than it would have been without that, without the background warming. Here are some fire weather records which were broken during 2021 during the heatwave event. So the black outline represents all the records in 2021 that were broken under or within the spatio-temporal extent of the heatwave. So, for example, Tmax, 14% of all records, that's the maximum daily temperature, were broken during 2021, and almost all of those records were broken during the heatwave event. And the same goes for the vapor pressure deficit shown in the middle. For the FWI, there was very few records, in fact, broken during 2021. And in fact, when we looked into the data a bit more closely, this was actually because even though temperatures were very high and relative humidity was very low, wind speeds were actually not particularly high. They were pretty average. And FWI is quite sensitive to wind speeds, particularly as the values get a bit higher. So in fact, the end result of that was that not many FWI records were broken. So I'm going to try to finish up here because I know we're running a little bit behind schedule. But another thing we could look at using the MODIS area burn product was the amount of total area burn which you can attribute to the heat dome. So if you look at all fire starts that occurred within the heat dome, that was responsible for about 21% of the area burned. Then if you extend the window by another 5 days, so any fires that start within 5 days of the heat dome leaving, it goes up to 28%, and for a 10-day window, it goes up to 34%. And in fact, during July 2021, 3.2 million hectares were burned in North America, which was more than any other single month on record. So I'm just going to finish up here and with what's happening currently. So I think it's probably well known that now that there's still extensive fire occurring in North America. Well, there were up to a few weeks ago. On the right, these are the hotspots for October up until October 26th, I think, when I took the screenshot. And there's still a lot of fire in October for Northwest Territories. This is basically unprecedented. I went back several years and there was very, very little fire activity. Even in 2014, which was a large fire year in Northwest Territories, by October, there was no fire or very little fire. And in fact, one of the things that happened is near Fort Simpson, a climate research station was burnt, essentially destroyed by wildfire. And as noted there, the founder says, "I can't escape the irony here. There should be snow on the ground." So I'm just going to leave it with that. And if anyone's got any questions, I'm happy to answer them. Thanks.
Thank you. That was excellent. Yeah. Really great. So we do have a couple questions. Do you think that the results and lessons learned, from looking at this North American perspective, could this be applied to Northern Europe or to Eurasia? Such a similar analysis, does the data exist? Do the I assume the methodologies could be applied, but applied there. Could you speak to that?
Yeah, actually, I'm working with we're working with a PhD student now to look at Western Europe. Of course, for Eurasia, it's a little bit more difficult because a lot of this analysis depends on having a good measure of daily fire spread. And we need to rely on a lot of satellite products, throughout Eurasia. So if anyone has any data, please get in touch.
I have some ideas about who might have some daily fire spread for Eurasia, but it'd probably be modeled. When you say Western Europe, do you also mean Northern Europe and the Nordics as well?
Yes. Yeah.
Okay. Excellent. In 2022, there was a heat wave in Europe. So how was it in North America?
2022, it was a reasonably busy fire season, but nothing obviously on the scale of the heat wave from 2021. Yeah, I think one of the stories of 2022 has been this late burning that, you know, usually everything quietens down by October. I mean, we had in Edmonton here, we had smoke a few weeks ago, right? So
Yeah.
In early October, and that's very, very unusual. I don't think I've been living here for 13, 14 years. I don't think it's happened before. So
Okay. And then I have a question. This is my kind of selfish question. I work a lot with researchers in Canada, and we often say, wouldn't it be great if we stopped putting borders or boundaries around the fire analysis between the US and Canada, so that we were doing more like you're showing, right? So all of our public communication and fire risk and smoke risk and air pollution was more continental based as opposed to country based. Do you have any thoughts on that?
well, I totally agree with that. But I guess most of my work, I guess I do put a border between the United States and Mexico, which I sometimes, you know, feel bad about because I am calling it North America. But the fire regimes down there are quite different, and a lot of focus of my research is mid-latitudinal weather. So, you know, we saw in 2021 that heat dome, you know, it didn't respect any boundaries. It was extensive fire throughout BC, Canada, and Oregon State, Washington, California. And that was the same weather event. So for me, it doesn't make sense to look at that without looking at it at a continental scale.
Yeah, and I think too, maybe this audience doesn't know, but the fire and smoke regimes from Mexico often impact the southern and central U.S., just as smoke from the southern and central U.S. can impact Mexico. So it's a connected continent, you know. So yeah, I agree. Rick noted in the chat that that in Alaska and Yukon territories and Northwest territories, that the combined wildfire for this year was the 7th highest since 1988. And 1988 was an extreme drought and heat wave, wasn't it? I'm a little young to remember that, but I think so. So,
1988 is just when the combined data is available from.
Oh, okay. All right, good. And then smoke in Alaska, for the audience, regularly originates in Siberia. Actually, smoke throughout Western Canada and the U.S. can often originate in Siberia, just as our smoke transports to Europe. So it is definitely a connected pan-boreal, pan-Arctic system. We ran a little late, but if all of our speakers could turn their cameras back on, and including my co-coordinator and co-host, Billy Becco, we just want to thank you all so much. This has been a very interesting, just amazing webinar. And even if I hadn't hosted it and helped plan it, I would still register and watch this because every talk has just been fascinating. So just one last round of applause to you. Thank you so much. This is amazing. And I hope our audience reaches out to you. And between these great speakers, you reach out to each other for collaboration, coordination.